Hello students, welcome to another video of number theory. Today we are going to discuss some theorems on arithmetic functions. First of all, we will take the definition of canonical form or the meaning of canonical form. Suppose the canonical form of n. Suppose this n is a integer, so we can write n in the form of prime raised to some power. As earlier we have seen, if n is any integer, then we can write n in the form of some prime raised to some power, p1 raised to alpha 1 into p2 raised to alpha 2 up to pr raised to alpha r. This definition we have seen in Euler's phi function. Before the Euler's phi function, we have seen the canonical expression of any integers where these pi's are primes, where these pi's are primes. For example, suppose n is equals to 90, then we can express this 90 as 2 into 45. Again we can express 2 into 45 is 3 into 15. Again we can express 15 as 2 into this 3 into 3 5s are 15. That is, we get the canonical expression of n is equals to 90. That is, the canonical expression of 90 is 2 into 3 square into 5. 2 into 3 square into 5. So, this is the canonical form of n or canonical form of this 90. So, from this step it is clear that this 2 is divisor of 90, again 3 is divisor of 90, 3 square is divisor of 90, 5 is again divisor of 90 and 1 is also divisor of 90. So, for this 3 raised to 2, if I write, this is just a rough work or necessary thing for the next theorem. Suppose this 3 raised to 2. So, from this we get the idea that 3 raised to 0 is divisor of 90, that is 1 divides 90. Again this implies 3 raised to 1 is also divisor of 90, since 3 raised to 1 is 3, 3 divides 90. Also we can write from this 3 square is also divisor of 90. So, from this we can write 3 square means, so I can write or generalize this as 3 raised to suppose some x divides 90. This is from this step 3 raised to x divides 90. So, there are 3 possibilities here. X is equals to suppose 2, this 3 raised to suppose 2 divides 90. This will give us, if I generalize this result, 3 raised to x divides 90, and there are 3 possibilities of x which are 0, 1 and 2. So, if I write 3 raised to x divides 90, and from this step or generalize this result, I can write 3 raised to x divides 90 and there are 3 possibilities of x which are 0, 1 and 2. So, from this if I write some p raised to alpha divides some number n, so from this I can write some p raised to suppose this alpha, suppose alpha p raised to beta divides, from this step p raised to alpha divides n. So, after that I can write p raised to some beta divides n, and there are alpha, here alpha is equal x is equals to 2. So, there are 1, 2 and 3 possibilities. So, there are alpha plus 1. So, this will give alpha plus 1 possibilities of beta, and which are 0 less equal beta less equal alpha. 0, 1, 2, 3 up to alpha, all are alpha plus 1 possibilities of this beta. So, this is useful in our next theorem. So, this is just a rough work, do not need to write in your notebook. So, theorem, next theorem is statement of the next theorem is, if n is equals to p1 raised to alpha 1 into p2 raised to alpha 2 up to pr raised to alpha r, then d of n, that is d of n is arithmetic function and d of n is the notation of divisors, all divisors of n. D of n is equals to alpha 1 plus 1, this alpha 1 plus 1 into alpha 2 plus 1 into alpha 3 plus 1 up to alpha r plus 1, or you can write it as product of alpha I plus 1 and I running from 1 to this r. This is the statement of next theorem. If you have given any number n and asked to find the d of n, then you are not going to find all the divisors of n, because of for larger values of n, for example 3000, 10,000, then there it takes lot of times to find the all divisors of suppose 10,000, 9,000, 6,000. So, you can just express that number in canonical representation, and using this theorem you can easily say that the total number of divisors or d of n is equals to whatever it may be. So, to prove this result, we have this d of n denotes number of positive divisors of n. D of n denotes the number of positive divisors of n. So, if n is equals to 1, then it is clear that this d of n is equals to 1, because 1 is the only divisor of n. If n is equals to 1, this will give d of n is equals to 1. Now, we have given if n is in the form, that is n is equals to p1 raised to alpha 1, p2 raised to alpha 2 up to pr raised to alpha r. Then from this we can use the definition of divisibility and say that this p1 raised to alpha 1 divides n, since n is multiplication of p1 raised to alpha 1 into some integer. So, using definition of divisibility, we can write p1 raised to alpha 1 divides n. This will give p1 raised to alpha 1 divides n. This is by using definition of divisibility. So, from this or from that rough calculation, from this result or from this, we can say that if p1 raised to alpha divides n, then p1 raised to beta divides n, and there are alpha plus 1, that is this number plus 1 possibilities that we have seen here. 3 raised to 2 divides 90, 3 raised to 2 divides 90, 3 square is 9 and 9 divides 90. So, from this we can write 3 raised to 0 is also divisor of 90, 3 raised to 1 is also divisor of 90, and 3 square is also divisor of 90. From this we can generalize this result, 3 raised to x divides 90, and there are 1, 2, 3 possibilities of x which are from 0 to 2. So, this from this we can write this p raised to suppose p1 raised to suppose f1 divides n, and this f1 is in between 0 to alpha 1, where 0 is less than or equals to f1 is f1 which is less than or equals to alpha 1. So, these are total alpha 1 plus 1 numbers, because if we count the numbers from 0, then alpha 1 plus 1, 1, 2, 3, 4, 5 up to alpha 1 and plus this 0 is again. So, alpha 1 plus 1, these are alpha 1 choices. So, here this f1 has alpha 1 plus 1 choices. Similarly, we can write this p2 raised to alpha 2 divides n. So, again we can write p2 raised to some f2 divides n, and this f2 is in between 0 to alpha 2, this less than or equals to alpha 2. Again this f2 has f2 has alpha 2 plus 1 choices. Here this f2 has alpha 2 plus 1 choices, and so on up. We can write this pr raised to alpha r divides n. So, this will give pr raised to some fr divides n, where this fr is in between 0 to alpha r. So, this alpha r has this, sorry, fr has alpha r plus 1 choices, alpha r plus 1 choices. So we can write total number of divisors are, so from the first step we can write there are alpha 1 plus 1 divisors, again from the second we get alpha 2 plus 1, and from the last we get alpha r plus 1 choices. So there are exactly multiplication of these alpha 1 plus 1 into alpha 2 plus 1 up to alpha r plus 1 choices. So therefore this alpha 1 plus 1 into alpha 2 plus 1 up to alpha r plus 1 are all divisors of n, are all divisors of n. Therefore we can write d of n is equals to alpha 1 plus 1 into alpha 2 plus 1 up to alpha r plus 1, or we can generalize this as product I running from 1 to r alpha I plus 1, alpha I plus 1. You can verify this result for any n, or you can check, or you get the proof better, or this multiplication of this alpha 1 plus 1, alpha 2 plus 1 up to alpha r plus 1 you will understand better from the example. So we will take one example. Find total number of divisors of 180. If the such questions asked, so we will must understand we have to find d of n, find total number of divisors. So here the solution we have given n is equals to 180. So 180 can be expressed as 2 into 90, and from the above, or we can just simplify this, 2 into 2 into 45, again we can write 2 into 2 into 3 into 3 into 5, or we can just write it as 2 square into 3 square into 5, 2 square 4, 3 square 9 into this 5. So here we get alpha p1 raised to alpha 1, p2 raised to alpha 2 up to p1 raised to alpha 1, p2 raised to alpha 2, p3 raised to alpha 3, and alpha 3 is equals to 1. So alpha 1 is equals to this, alpha 2 is equals to this, alpha 3 is equals to this. So using this result we can write d of 180 is equals to, therefore d of 180 is equals to alpha 1 plus 1, alpha 2 plus 1, alpha 3 plus 1. Just a second. So after this, right here, next line, right, alpha 1 is equals to 2, alpha 2 is equals to 2, and alpha 3 is equals to 1, alpha 1, alpha 2, alpha 3. So using this result we can write d of 180 is equals to, here alpha 1 is equals to 2 plus 1 into this 2 plus 1, and alpha 3 is 1 plus 1. So 3 into 3 into 2, so 3 is 9, 2 is 18. So there are 18 divisors of 180. So d of 180 is equals to 18. Hence you can verify the result. Now next topic is, next definition is definition of multiplicative function. Next definition of multiplicative function. Definition of multiplicative function. A function f is said to be multiplicative. A function f is said to be multiplicative if f satisfies this property, that is f of ab is equals to f of a into f of b. You have seen the definition of homogeneous function. So this is just the condition of homogeneous function for multiplication. A function f is said to be multiplicative function if f satisfies this property, that is f of ab is equals to f of a into f of b. That is function of multiplication of any two values is just the multiplication of function of that two values. F of a b is equals to f of a into f of b. So we will prove the next theorem. We are going to use this result or this definition in next theorem. Next theorem is d is multiplicative function, that is arithmetic function d is multiplicative function. D is multiplicative function, that is a function f is said to be multiplicative. So d of mn is equals to d of m into d of n, where GCD of m and n is equals to 1. Function f is said to be multiplicative. Now to prove this d is multiplicative function, d means number of all positive divisors of some number n. So here let us take m is equals to just p1 raised to alpha 1, p2 raised to alpha 2 up to pr raised to alpha r, and n is equals to suppose q1 raised to beta 1 into q2 raised to beta 2, this just beta, up to qs raised to beta s, qs raised to beta s. So this is the canonical representation of m and n. Our claim is d of mn is equals to d of m into d of n. Here this is the canonical representation, means this where these pi's and qi's are pi's and suppose this qj are primes, these prime numbers. So our claim is d of mn is equals to d of m and d of n. Now we have m is equals to this, n is equals to this. So we can write m into n is equals to just the product of this, that is p1 raised to alpha 1, p2 raised to alpha 2 up to pr raised to alpha r into q1 raised to beta 1 into q2 raised to beta 2 up to qs raised to beta s. So this is multiplication of mn, that is mn can be expressed as canonical form. So this is just the canonical form of m into n. But we know that the previous theorem, we know that d of m is here p1, m can be expressed as canonical form of this. So we can write d of m is alpha 1 plus 1 into alpha 2 plus 1 plus up to alpha r plus 1. So alpha 1 plus 1 into alpha 2 plus 1 up to alpha r plus 1, and you can write d of n as this beta 1 plus 1 into beta 2 plus 1 into beta s plus 1. So this d of m and d of n. So we can write d of m into d of n. From this mn we can write d of mn, d of m into n. D of mn will become our alpha 1 plus 1 into alpha 2 plus 1 plus up to alpha r plus 1 into beta 1 plus 1 into beta 2 plus 1 plus up to beta s plus 1. Here this we can write just d of mn is equals to product of alpha 1 plus 1 alpha 2 plus 1 up to beta s plus 1, because of GCD of m and n is equals to here given GCD of mn is equals to 1. If GCD of m and n is equals to 1, so we can write m into n is equals to, that is, just take one remark before this, so it will make clear. So write one remark before this theorem. Sorry, remark. If GCD of mn is equals to 1, then this set, then the set of positive divisors, of suppose mn, positive divisors of mn consist of consists of all positive divisors of m and n, all positive divisors of product elements instead of m and n, right? Product elements, suppose d1 d2, product elements d1 into d2, such that this d1 is divisor of m and d2 is divisor of n. That is, if GCD of mn is equals to 1, then all divisors of mn are just the multiplication of divisors of m and divisors of n. Here d1 is divisor of m, d2 is divisor of m, so divisor of mn. If GCD of mn is equals to 1, then divisors of m into n are just the divisors, multiplication of these divisors, d1 into d2. So we can write here divisors of mn are p1 raised to alpha 1, p2 raised to alpha 2 up to into this multiplication, because GCD of m and n is equals to 1. Since GCD of m and n is equals to 1, here we have taken the multiplication, or we have just written the canonical expression of m into n. Here m into n, we have canonical expression of m is this and canonical expression of n is equals to this, and just written the canonical expression of m into n is equals to is like this, or just multiplication of these two canonical expressions, because GCD of m and n is equals to 1, which is given in our statement. So if GCD of m and n is equals to 1 and m into n is the multiplication of m and n, then we can write the divisors of m into n are multiplication of divisors of m and n. So using this result, we have this. Now here d of m is equals to this and d of n is equals to this. So from this equation number, suppose this is equation number star. So from this we can write the d of m, and equation number, suppose this a, capital A, instead of star write it as equation number A, and this is equation number of capital B. Therefore from equation 1 and from equations A and B, from equations A and B, we can write d of mn is equals to d of m into d of n. Hence our d is multiplicative function. Hence the proof.